Have you ever wondered how your computer's CPU manages to handle so many tasks at once? What actually happens inside Linux when you kill a process? Why do C or C++ programs return a number when they exit? And why does pressing the power button to shut down your computer sometimes cause you to lose data? In this video, we're going to dive into these questions and much more. After you watch this video, you'll get an assignment, where we'll keep building your AI-powered shell. When you run a Python or Node.js script, your AI shell will automatically help you fix any errors you run into. The goal of this series is to pack an entire university-level computer science course into just 6 months. By the end of it, you won't just learn the basics. You'll have advanced skills that will let you be a full-stack developer with AI as your assistant. It usually takes years to reach this level, but we're going to make it happen in a much shorter time. But remember, to get the most out of this, it's really important to not just watch the videos. Make sure you complete all the assignments and projects. Alright, let's jump in. Understanding how Linux processes work might seem tricky at first, especially if you're new to coding. But don't worry, let's take it step by step, using the first principles thinking approach, which we always use to solve complex tasks. We'll start with some simple ideas, and I'll make sure everything is clear, even if you've just started learning this week. Think of the CPU as a device that runs on DC power or a battery. Now, imagine you've connected a light bulb to the battery. To make the light blink at a steady pace, we need to control the timing. So how do we get the light to blink consistently with just a battery? You might remember from physics class that a pendulum in a grandfather clock swings back and forth at a regular, consistent pace. This design helps the clock keep time accurately. In nature, this kind of pattern shows up often in different fields. For instance, if you apply voltage to a quartz crystal, it vibrates at a very stable and precise frequency. Without losing energy, these vibrations can keep going reliably over time. We use the same idea to give our light bulb a heartbeat, making it blink at a precise rate, just like the pendulum in a clock. Every CPU has something called a crystal oscillator. This is a tiny electronic part that uses the vibrations of a quartz crystal to create a stable, precise frequency. You can think of this crystal oscillator as the heartbeat of the CPU. It keeps the CPU running in sync, just like a heartbeat keeps our bodies in rhythm. Thanks to this steady pulse, the CPU can perform all its calculations and operations smoothly and on time. In short, the crystal oscillator's clock signal sets the tempo for everything the CPU does, helping it work consistently. Modern CPUs operate at frequencies between 2.5 GHz and 3.5 GHz, or even higher. This frequency refers to the speed of the CPU's crystal oscillator, meaning the CPU can complete 2.5 to 3.5 billion cycles every second. In a CPU, one cycle is often called a tick or a clock cycle. Each instruction in your code takes one or more cycles to execute, depending on how complex it is. To keep it simple, let's assume that each instruction only takes one clock cycle. If we use an assembler simulator, we can actually see how each instruction is executed with every tick of the CPU. When we adjust the clock speed in the simulator, you'll notice that the code runs faster at a higher frequency. This means that the faster your CPU is, the faster the crystal oscillator is ticking. But the CPU needs to be designed to handle higher frequencies. Otherwise, it can start making errors. When you hear about overclocking a CPU, it's about increasing the frequency of the crystal oscillator. Modern CPUs can handle many tasks at once. Even though it seems like everything is happening simultaneously, what's actually happening is the CPU is switching between tasks so quickly that it feels instant to us. To help make sense of this, think about how humans perceive visual and sound information. When watching a video, displaying 25 frames per second is enough for our eyes to see smooth, continuous motion. Similarly, if audio is processed at more than 8,000 cycles per second, it sounds clear and seamless to our ears. A lot of what a CPU does is designed to interact with humans. For example, if a website loads in 0.2 seconds, we'd consider that fast. In real-time applications like gaming or video calls, a latency between 1 and 20 milliseconds is ideal for smooth performance. CPUs can handle far more tasks in 1 second than we can even notice. For background tasks that don't need immediate attention, the CPU can delay them while it deals with more urgent operations. So how does the CPU manage to run multiple tasks at the same time? It's all thanks to the Linux kernel, which is responsible for creating, managing, and scheduling processes. The kernel divides CPU time into small segments called time slices, or quanta. Each time slice represents a short period of CPU time that is dedicated to a specific task. The number of CPU cycles in a time slice depends on the CPU's frequency and how long the time slice lasts. In modern systems, a time slice can include tens of millions or even hundreds of millions of CPU cycles. You can think of a time slice as a small slice of the CPU's time. In systems like Linux or Windows, time slices typically last just a few milliseconds, but their exact duration can change depending on the priority of the task and the system's workload. Why only a few milliseconds? This is similar to 100 frames per second, which is a common frame rate for gaming or high-performance displays. The idea is that tasks are processed smoothly and efficiently, just like a high FPS makes video games look seamless. However, time slices are dynamic, meaning their length changes depending on the task and the scheduling algorithm that the kernel uses. The Linux kernel adjusts the length of time slices based on the needs of different tasks. For example, high-priority tasks may get longer or more frequent time slices, allowing them to run faster. On the other hand, lower-priority tasks get fewer or shorter time slices, which makes them run slower. This dynamic system ensures that the CPU can handle all tasks efficiently. Critical tasks get immediate attention, while background tasks are still managed. High-priority tasks seem to run faster because they get more CPU time, while lower-priority tasks receive less, making them run more slowly. In Linux, task prioritization is key to ensuring time-sensitive tasks like interacting with the user interface, playing videos, or gaming run smoothly without any delays. These tasks need to happen immediately to provide a seamless experience. For example, when you move your mouse, click a button, or play a video, the system processes those actions in real time. To manage this, Linux uses different priority levels for normal tasks and real-time tasks. Normal tasks are non-critical, meaning they don't have strict deadlines. The scheduler balances their execution based on system load and fairness, ensuring that all processes eventually get CPU time. Common use cases include background processes, general-purpose applications, and tasks that can tolerate some delay or variability in execution time. Real-time tasks are critical because they must be completed within a strict time frame. The system prioritizes them to avoid delays that could affect performance, such as in audio/video streaming, gaming, or industrial control systems. Normal tasks have a nice value that ranges from -20 to +19. A lower nice value means higher priority, as the task is less nice to other processes, so it demands more CPU time. Real-time tasks, on the other hand, have a priority range from 0 to 99. The higher the number, the higher the priority. Real-time tasks are critical in systems where precise timing is important, like gaming, video processing, live chat, or other multimedia tasks. These tasks need to meet strict deadlines to avoid issues like dropped frames in videos or audio glitches. In gaming, the CPU has to prioritize tasks like rendering images and processing user inputs like mouse clicks and keystrokes. A smooth frame rate of 60 FPS or higher is important for fluid visuals. Similarly, audio playback has to be processed at the right rate to avoid interruptions. You can use the Linux shell command top to view the priority of processes. In the output, the PR column shows the priority, and the NI column shows the nice value. Alternatively, you can use the PS command to see the process ID, command name, priority, and nice value for all running processes. In a Linux system, there can be many processes running at the same time. Some are system processes, which are part of the operating system, and others are user processes, like your Hello World program. For security reasons, each process is given its own memory space. This means one process can't access the memory of another. So if you run multiple instances of your Hello World program, each one works separately. They can't read or write each other's variables in memory. Now, as each process uses up memory, what happens if the total memory used by all processes is more than the available physical memory? There are two possible situations. The first is using memory swap. The system moves some data from the RAM to the disk, using part of the disk as extra memory. The second is no swap memory. If there's no swap memory available, the system might crash because there's no more memory to use. By default, when you set up an AWS EC2 instance, swap memory isn't turned on. Swap memory acts like an extension of your RAM, letting your instance handle more tasks, even when the RAM is fully used. Let's walk through how to create and enable swap memory on your EC2 instance in a few easy steps. First, we'll create a swap file. This is like setting aside some storage space to be used as extra memory. Run this command to create a 2 GB swap file. Here's what's happening. DD is a tool that copies data from one place to another. We use it to fill a file with zeros, which will be used as our swap space. IF is the input file providing the zeros, and OF is the name of the file we're creating. We set BS equals 1M for the block size, 1 MB, and count equals 2048 to make it 2 GB. Next, we need to make sure only the root user can access the swap file for security reasons. This chmod 600 command changes the file permissions so only the root user can read and write to it. No other users can access it. Now let's tell the system to use this file as swap space. The mkswap command formats the file so it can be used as swap space. It's like telling the system, this file is reserved memory. Use it when needed. Once the file is ready, we'll enable it so the Linux kernel can start using it. Finally, to ensure the swap file is enabled every time your instance restarts, we'll add it to a configuration file called etc/fstab. This command adds the swap file entry to the etc/fstab file. This way, the swap file is automatically activated whenever the system reboots. Keep in mind that disk storage is much slower than physical memory. In AWS EC2, the storage is often network-based, which can be slower than modern SSDs. If your processors need more memory than your physical RAM can provide, enabling swap memory helps avoid system crashes. The Linux kernel manages memory efficiently, swapping out data that isn't being accessed as often. Each process in a Linux system has its own memory space. But how do multiple processes share the same CPU? Well, the CPU has a limited number of registers, so it's impossible for each process to have its own dedicated set of registers. So what happens? The Linux kernel manages this by performing something called context switching between processes. When a process is paused or stopped from running on the CPU, the Linux kernel saves all the data from the CPU registers into memory. This data is stored in a special structure called the process control block in memory. A process control block, PCB, also known as a process descriptor, is a data structure that holds all the important information about a process. Here are some of the key fields that you'll need to understand. Process state. It shows whether the process is running, paused, or in another state. Process ID. A unique identifier for the process. Program counter. Stores the current location of the code instruction being executed. Registers. Holds the data from the CPU registers when the process is paused. Pending signals. signals waiting to be processed when the process resumes. Now let's talk about how context switching works, or how we suspend and resume a process. When a process is paused, for example during multitasking or while waiting for input-output, the CPU's current state, such as register data and the program counter, is saved in the process's PCB. This allows the process to resume later exactly where it left off. When the process is ready to run again, the kernel restores the saved register data from the PCB, ensuring the process continues from the point it was paused, with its previous state and context fully intact. By saving and restoring the CPU state during context switching, the Linux kernel enables different processes to share the same CPU without interfering in each other's tasks. On average, the size of a process control block in modern operating systems is between 1 kilobyte and 2 kilobytes, though the actual size can vary depending on the system's complexity, architecture, and the specific data stored for each process. However, frequently reading and writing data during context switches can become a bottleneck, impacting performance. This is why, in some cases, a single process application can be more efficient than a multi-process one. There's less context switching, reducing the overhead on the system. For example, the popular web software system Apache uses a multi-process model where each request is handled by a separate process. This causes more context switches. On the other hand, many companies have moved to Nginx, which uses an event-driven single-process model. This allows Nginx to handle many connections within the same process, cutting down on overhead and boosting efficiency, especially in high-traffic situations. In Linux, processes can communicate with each other in various ways, and one of the simplest and most common methods is through signals. A signal is a feature provided by the Linux kernel API that lets the operating system notify a process when a specific event happens. Signals can interrupt a process and alert it to events like user actions, for example pressing Ctrl-C, errors, for example division by 0, or system events, for example a timer running out. There are two main types of signals: hardware signals, also called interrupts, and software signals, known as traps. Interrupts are signals sent to the CPU by external hardware, like a keyboard or network card, to indicate that something needs immediate attention. For example, pressing a key on the keyboard, receiving a network packet, or a timer expiring can trigger an interrupt. When an interrupt occurs, the CPU temporarily pauses its current task to handle the event and then resumes normal operations once it's done. Traps are software interrupts, triggered by the currently running program. They're used when the program needs the operating system to perform a service, like opening a file or starting a new process. Traps can be intentional, such as making a system call, or unintentional, like division by 0 or trying to access invalid memory. When a signal is sent to a process, such as a termination request, like sigterm, or an interrupt, the process will handle it in one of two ways, depending on whether it's running or suspended. If the process is running, the signal will be handled immediately by its signal handler. If the process is suspended, the signal is marked as pending in the PCB. When the process resumes, the Linux kernel first processes any pending signals before letting the process continue its work. This system ensures that processes can quickly respond to events, whether they're triggered by hardware or software, and it allows processes to communicate smoothly in a Linux environment. In C, the main function returns an integer when the program finishes, because it gives a way for the program to communicate its result to the operating system, or the process that called it. This return value tells whether the program ran successfully or if something went wrong. Return 0. This usually means the program ran successfully, without any problems. By convention, returning 0 means everything worked as expected. Non-zero return values. Any non-zero value generally means there was an error or the program didn't finish properly. Different non-zero values can be used to represent different types of errors, and you can define what each value means in your program. When the program ends and returns a value from the main function, the operating system looks at this return value, called the exit status, to figure out how the program ended. This is especially useful in automated systems, or scripts where you need to know if the program succeeded or failed. Here's an example of a simple C program and a bash script that shows how to capture the return value, also called the exit status, from a C program. To run this C program, you first need to compile it. You can do that with the GCC compiler like this. Now here's a bash script that runs the compiled C program and checks the return value. Let's break down the code. The first line uses a hash key and an exclamation mark to tell the system that the script should be run using the bash shell. $example runs the compiled C program, and $? is a special variable in bash that holds the return value or exit status of the last command executed. In this case, it's capturing the return value of the C program. The script checks if the return value is 0, which means the program ran successfully. If the value is anything else, the script assumes there was an error and prints the exit code. This is how you can use a bash script to check whether a C program ran correctly or if there was an error. In a Unix-like shell, managing processes efficiently is key. Whether you're running a program in the foreground or background, knowing how to control and monitor them can save you a lot of time. Let's start with running commands in the background. Normally, when you run a command, it takes control of your terminal. But if you want to keep using the terminal while your command runs in the background, you can add an AND at the end. This way, the program runs in the background, and you can continue working in the terminal. If you're running a process in the foreground, meaning it's using your terminal session, you can stop at any time by pressing Ctrl-C. This sends a signal to the program to terminate it. Just press Ctrl-C and it will stop. Normally, when you close the terminal, any running processes also stop. But what if you need your program to keep running after you log out or close the terminal? You can use the no-hop command, which stands for no hang-up. It keeps your program running even if the terminal closes. With no-hop, your program runs in the background, and its output gets saved to a file called nohop.out, unless you specify a different file. Sometimes you might want to check which processes are running. One way to do this is by using the ps command, combined with grep to search the processes by name. This lists all running processes and filters the results to show only those with the name myprogram. To stop a process, you can use the kill command. First, you'll need the process ID, which you can find using the ps and grep commands. By default, kill sends a polite request for the process to stop. If the process doesn't stop, you can force it to terminate with the sig kill signal. Lastly, if you have multiple instances of a program running and want to stop them all, you can use the kill all command. This will send a termination signal to all processes with the same name. This command stops all instances of my program. When you power off your computer by pressing the power button, the system doesn't have time to save data from memory to storage, like a hard drive or SSD. This increases the risk of losing unsaved work. It's similar to using the halt command in Linux, which immediately stops the CPU without shutting down safely. To avoid this, it's better to use commands like reboot, shutdown, or power off. These commands send signals to all running processes, giving them time to close properly and save data. Most applications and system processes are built to handle signals like sigterm and sigkill. When a process receives a sigterm, it has a chance to finish its work, save data, and exit cleanly. If it doesn't respond to sigterm, the system might send a sigkill, which forcefully stops the process without giving it time to clean up. By using these commands, you help prevent data loss and ensure your system remains stable. There are also two important concepts in the Linux operating system: threads and coroutines. Threads, like processes, have a PCB that stores important information about their execution. However, the key difference is that multiple threads within the same process share the same memory space. This shared memory allows threads to work more efficiently together, since they can easily access and modify the same data. But this also means that if one thread misbehaves or encounters an issue, it can affect the other threads within the same process. Coroutines, on the other hand, are even more lightweight than threads. They're managed in user space, meaning they don't require the operating system's kernel to manage them. This makes coroutines faster and more efficient in certain scenarios. We'll dive deeper into these concepts in later videos. In the description of this video, you'll find a link to join our Discord server. Once you're in, you'll get hands-on support and can explore everything we talked about today in more depth. Our AI assistant, ByteMate, will guide you through an interactive assignment to help you practice concepts like process management, memory management, and signal handling. By completing the assignment, you'll continue building your AI-powered shell. When you run a Python or Node.js script, your AI shell will automatically help fix any errors you might come across. This helps give you practical experience managing Linux processes while learning how to use AI to tackle common coding problems. Whether you're just starting with Linux or want to improve your skills, this assignment will help you apply the key Linux process concepts we covered in this video. Don't forget to like the video, subscribe, and hit the notification bell so you don't miss any of our lessons on Linux, AI, and full-stack development. See you next time!